Hello everyone, section 11.5, volumes of spheres and cylinders. I want to first explain Cavalieri's principle. Cavalieri's principle is best shown by this diagram here. The volume of this stack of papers and the volume of this stack of papers is exactly the same because the stack hasn't changed except we've just taken it and slanted it, right? The Cavalieri's principle states that the cross-section at each height is the same. So the cross-section in this stack of papers is each slice of paper, and the cross-section in this stack of papers is also each slice of paper. They're always congruent, they're always equal, and the height of this stack of paper and the height of this stack of paper is always equal. Therefore, the two volumes are equal, and that's what Cavalieri's principle is saying down here. Okay, the volume of each shaded cross-section below is 6 centimeters squared. Since the prisms have the same height, then all three of these prisms have the exact same volume. Okay. Example 1. Find the volume of each prism, part A. So I could try to find the volume of this base and then try to multiply it times this height. It's way too confusing. Try to think of this triangle here as the base of the prism and the height as the 3 centimeters. So what is the area of the base of this prism? So the area of this base is height of the triangle times base of the triangle divided by 2. 40 divided by 2 is 20. So volume of this prism equals 20. So right, 5 times 8 is 40, divided by 2 is 20, times the height of the prism, which is 3. So the volume of this prism is 60 centimeters cubed. Part B, again, I could try to think of the base as this square down the bottom, or this rectangle down the bottom, and then the rectangle on the top, and then try to, it's too complicated. Just because it's drawn like this and this looks like the height of the prism doesn't mean that it has to be the height of the prism. So the base of this prism is going to be this trapezoid, because this trapezoid is congruent to this trapezoid in the back, and the height of this prism is going to be 4.2 meters. So let's first find the area of the trapezoid. So get that off the screen. Area of the trapezoid equal 1/2 base 1 plus base 2 times the height of the trapezoid. 1/2 4.4 plus 5.6 times 2.5. 4.4 plus 5.6 is 10. Half of 10 is 5. 5 times 2.5 is equal to 12.25, I think. 5 times 2.5, 12.25, like I said. 12.5 meters squared. That's the area of the base of volume. A little bit of space here. Volume of the prism. Area of the base times the height of the prism, not the height of the trapezoid or the height of the triangle over here. Height of the prism equal to 12.5 times 4.2 times 4.2 gives us 52.5 meters cubed. Sorry. Okay, there's example 1. Now, so that was volume of a prism. Volume of a cylinder is exactly the same. Area of the base times the height. You could try to simplify the formula, but I don't think this is more simple. I think this is more simple, because this volume formula is exactly the same as the volume formula for a prism. Area of the base times the height. Remember one formula for the two objects. Okay, example 2. So what is the area of the base? Well, the base here is this circle. Area of the base is pi r squared. So volume of the cylinder equals area of the base times the height. Area of the base here is 25 pi, and the height is 9.1. Even though it's turned sideways, that's still the height. So 25 times 9.1 equals 227.5 pi meters cubed, or approximately, times that by pi, multiply by the pi key, giving us 714.7 meters cubed. And again, on a quiz or test, it would tell you whether they want it in terms of pi, or if they want it rounded to nearest tenth, nearest hundredth, nearest whole number, whatever they tell you to round to. Okay? It doesn't say in this problem, so I'm just going to do both. Part B, area of the base. Let's work over here. Volume cylinder equals area of the base times the height. Area of the base is 49 pi, and the height 22. Even though this is oblique, it's lean, it doesn't matter. It's still going to have the same volume. That's Cavalieri's principle. So 49 times 22 equals 1,078 pi cubic feet, or feet cubed, or approximately, multiply that times pi times the pi key, 3,386.6 cubic feet, or feet cubed. That's example 2. Example 3 is going to use this formula for density. Okay, density is equal to mass divided by volume. So we use that in this formula. Example 3, the density of water is 1,000 kilograms per cubic meter. Mass over volume. So kilograms is mass, cubic meter is volume. So 1,000 kilograms per cubic meter. Find the mass of 1 cubic foot of water. So if we have, and use the fact that 1 foot is equal to 0.3038. That's 1 foot, not 1 cubic foot. Okay, so 1 foot equals 0.3038. Then 1 cubic foot meters is equal to 0.3038 cubed, 0.0280 meters cubed. Okay, we want to find the mass of 1 cubic meter. 1 cubic foot, which is this many cubic meters. Okay, so the density, D, equals M over V, which means that if we multiply both sides by V, M is equal to dV. Mass is equal to 1,000 kilograms per cubic meter times the volume. 1 cubic foot, we just found out, is 0.0280 meters cubed. 0.0280 meters cubed. So I want you to notice something here. Meters cubed, meters cubed cancel. I'm left with kilograms. 1,000 times 1,000 gives us, and this is just going to move the decimal point over, 28.6 0.04 kilograms. That's our mass. That's what's left. Did I want to point out the kilograms over meters cubed, canceling? Because that leads us into this very next problem, which is how we're going to do this next problem. This problem is tricky. I used to give this as a challenge problem for students to work on over a long period of time, but here I just want to show it to you as an example. And it's not something that you're going to be able to find the answer for without doing some research or knowing some calculus, but that's not what I'm looking for in this problem. I'm looking for you to create a possible, just a possible, not the formula, just a possible formula for the time, which is going to be measured in seconds. We're going to use t to measure as a variable for time, which is going to be measured in seconds, that takes water to completely drain from a cylinder. What do we know? The known variables and constraints are the area of the base of the cylinder. So we know the area of the base of the cylinder is capital B, and that's measured in square meters or meters squared. We know the area of the hole right here, which is little b, and little b is measured in meters squared again. We know the density of water, which is rho. It's a Greek letter. So that's measured in grams per cubic meter, so 1 gram per cubic meter. Okay, and that's the same thing as what I had in the previous problem. 1,000 kilograms per cubic meter is the same as 1 gram per cubic meter. The height of the water, labeled h, variable h, and that's going to be measured in meters. We know what gravity is. Gravity is 9.8 meters per second squared. That's a constant on Earth at sea level. It changes different places, but for the most part, 9.8 meters per second squared is a constant. And we want this formula needs to make sense mathematically. Okay, you don't need to go to the internet. You don't need to find out. You don't need to plug this in and find out what the formula is. All I want the formula to do is to make sense mathematically. What does that mean? Well, what are we looking for in the end? What is the goal of this problem? What are we trying to find? So we're trying to find time. Time, which is measured in seconds. This is important because, like in the previous problem, when we were trying to find mass in this particular problem was measured in kilograms. Our final answer has to be in kilograms. If it's anything other than in kilograms, then we haven't found mass. So our formula has to give us something that is measured in seconds in the end. It can't be meters, there can't be grams, there can't be anything. It can't be seconds squared. There has to be seconds only in the end. So if our formula doesn't give us just seconds in the end, then the formula doesn't work. It's not a possible formula. Okay? So back to the problem. We want time in the end. What do we have? Okay, we have capital B measured in meters squared. We have little b measured in meters squared. We have height measured in meters. We have density, rho, measured in grams per meters cubed. We're doing grams this time, not kilograms. And we have gravity, which is measured in meters per second squared. Okay, so let's think about this logically. In this problem, just like in the previous problem, we're going to be canceling out certain units, and the end result has to be seconds. So of all these things that are in here, there's one thing that absolutely has to be in our formula, And there's one thing in here that absolutely cannot be on our formula. And I want you to think about those two questions, right? Or those two things right now. What's one thing that absolutely has to be in our formula? And one thing that absolutely cannot be in our formula. Thinking about what our goal is to have a formula that gives us seconds only in the end. We just want seconds in the end. We're going to be canceling certain things out, and we only want seconds in the end. So what's the one thing that has to be in the formula? And these are the only things that we've got. Capital B, little b, h, rho, and g. These are the only things that are possibly going into our formula. We're not putting anything else in. We're not creating our own variables. We're not doing anything else. This is it. So what's the one thing that absolutely has to be in our formula and the one thing that cannot be in our formula? So the one thing that absolutely has to be in our formula is gravity. It's the only thing in all of these that has seconds in it. If we want seconds in the end, gravity is the only thing that has seconds in it. There has to be gravity in our formula. What's the one thing that cannot be in our formula? Absolutely positively cannot be in the formula. Of the remaining things, what can't be in our formula? Rho. Density of water can't be in our formula. It's not going to play a role in the time it takes to empty out this cylinder with water. Rho can't be in our formula because we have absolutely nothing that's going to cancel grams in the end. There's nothing else that has grams in it to cancel grams so that we don't have grams in our final answer. Remember, our final answer is only going to have seconds. It's not going to have anything else. Okay. So we now know rho is not part of this equation. It's not part of this formula. What is? Gravity is. This is measured in meters per second squared. That's seconds in the denominator. Our final answer is going to have seconds in the numerator, not in the denominator. So how do we get seconds from a denominator into a numerator? Well, we put gravity in the denominator. What do we have so far? This is 1 over meters per second squared. 1 divided by a fraction. We don't divide by fractions, we multiply by the reciprocals. So 1 times second squared over meters. 1 times second is seconds squared over meters. This is what we've got so far, if we have this, right? Close. What don't we want? We don't want the meters in there. How can we cancel meters? What can we do to this m to get rid of this m? What do we have? We've got a b, a capital B, a little b, and a capital H. Meters squared, into meters. What will cancel with this meters? Height. If we multiply this times m, these m's will cancel. We multiply this times height. Now I have seconds squared. Close. Not there yet. What do I need? I don't want seconds squared, I want seconds. How do I go from seconds squared to seconds? Square root it. This gives me a formula in seconds. Now, this is just one possible formula. What are other possible formulas? Well, I never used the capital B or the little b. And these units cancel each other if I put one over the other, right? So I could put, and this is just another possible answer, capital B over little b. Or I could put, it's another possibility, inside, capital B H over little b G. Or I could put little b over big B. These could be reciprocated. Those don't matter. Okay, these are possible formulas. Okay, so I believe that there are 4 possible formulas that could work here. Okay, 4 different variations of these. I don't care which one is the actual one. I'm just saying that these are the ones. So what are the others? The others are little b over big B, square root H over G, and little b H over big B G. Okay, these are our possible formulas. You only have to find one of them. I don't know. It doesn't matter which one actually is the one that works. That would take a lot more than what we can do. There's calculus involved. I will tell you that there's a square root of a constant number that's involved in there, not the 9.8. There's something else that's in there when you do the calculus. But these are the possible choices because this gives us seconds, this gives us seconds, this gives us seconds, and this gives us seconds. And that's all we wanted to find. So that's example 4. Example 5. You're building a cylindrical packing tube. You want the length of the tube to be 30 inches and the volume to be 589 cubic inches. What should the radius of the base be? Okay, so volume equals, so volume of a cylinder equals area of the base times the height. Okay. The volume is 589 cubic inches. Area of the base, the height is the length of 30 inches. Okay. Divide by 30. Capital B equals 589 divided by 30 is 19.63 repeating. So this is the area of our base. This is square inches now, not cubic inches. But we want to find the radius. So what is the area of the base formula? Pi r squared equals 19.63 repeating. Divide both sides by pi, so divide by my pi key. R squared equals 6.24948 ... I want to know what r is, so square root both sides. Approximately 2.5 inches. Example 6. You're building a 3-foot tall dresser. You want the volume to be 42 cubic feet. What should the area of the base be? So again, we know volume of prism is equal to area of the base times the height. Notice I didn't memorize another formula, just know it's area of the base times the height. We want the volume to be 42 area of the base. The height is 3 feet. 42 divided by 3 is 14. So area of the base is equal to 14 square feet, or feet squared. Okay, so that's the answer to the question. Now it says give possible length and width. So really we could do 1 by 14. Could be 1 foot deep and 14 feet wide and 3 feet tall. 2 by 7, 2 feet deep. So we could do 1 foot by 14 feet. Seems unlikely, but 2 feet by 7 feet. Could be. Maybe this is one of the really long dressers that has the mirror behind it. Possibly. Those are the only ones that are going to give us nice whole numbers, right? Because those are the only factors of 14. So I don't want to go into any others, 3 by something, 4 by something. But those are possible lengths and widths. Okay. All right. This next part here is to illustrate similar solids. And most of my students, when they first look at these pictures, just look at them and don't read this thing here, and they certainly don't look at the pictures really closely and notice that these people aren't really big, that these buildings are really small, and those are people in the backgrounds here. So that's a person there and there. These are people here. This is a miniature city with working railroads and cars and boats and things like that to illustrate similar solids. Now, I don't usually go through these examples that are done for you, but I want to for this problem because it's going to lead us into a concept that I have at the bottom of the page here. So the table below shows the ratios of the perimeters and areas and volumes for a pair of similar cylinders shown at the left here. So we have a cylinder that's 12 tall. Cylinder 1 is 12 units tall and 6 units radius. Cylinder 2 is 8 units tall and 4 unit radius. Okay. Volumes, areas and volumes for the pair of similar cylinders. So I'm telling you they are similar. Shown on the left, what do you notice about the ratios of the cylinders? So they're similar because 6 to 4 and 12 to 8 are exactly the same. 6 to 4 reduces down to 3 to 2, 12 to 8 reduces down to 3 to 2. The scale factor, or similarity ratio, and I should change this, the similarity ratio is 3 to 2. And the scale factor might be 3 to 2 if I'm going from this one to this one, but it's 2 to 3 if I'm going from this one to this one. So maybe I'll change the wording on that. So scale, we'll continue with what I've got written here, and I'll change maybe at some time to similarity ratio. Scale factor 3 to 2. Okay. The perimeter, the base perimeter of cylinder 1, the perimeter of a cylinder, the perimeter or circumference here is 12 pi, 2 pi times 6. The perimeter or circumference of base 2 is going to be 8 pi. These reduce down to 6 to 4 or 3 to 2. So the similarity ratio is 3 to 2. The ratio of the perimeters is 3 to 2. Okay, lateral area. And we'll get into what lateral area is in a little bit, but for now, let me just tell you. Lateral area of figure 1 is circumference times the height. So the circumference we said was 12 pi times 12. So 2 pi times 6, or 12 pi times 12. And lateral area of figure 2, circumference times the height, or 8 pi times 8, right? Or 2 pi times 4, which is 8 pi times 8. These reduce. 2 pi, they're gone. We got a lot of reducing. It goes down here, reduces down to 9 over 4. 9 over 4 is 3 squared to 2 squared. So similarity ratio is 3 to 2. The ratio of the perimeters is 3 to 2. The ratio of the lateral areas is 3 squared to 2 squared. Volume of the first figure, first cylinder. Area of the base, 36 pi times the height, 12, right? 36, 6 squared, times pi, times 12. Volume of the second cylinder, 16 pi times 8, 4 squared is 16 times pi times 8. Pi's cancel. A whole bunch of reducing goes on here, and we end up with 27 over 8. 27 over 8 becomes 3 cubed to 2 cubed. Similarity ratio is 3 to 2. Ratio of the perimeters is 3 to 2. Ratio of the areas is 3 squared to 2 squared. Ratio of the volumes is 3 cubed to 2 cubed. Which leads us into this. If we know the similarity ratio is A to B, then the ratio of the areas must be A squared to B squared, and the ratio of their volumes must be A cubed to B cubed. Example 7. Square prism A and square prism B are similar. So we're told that they're similar right from the beginning. Each base edge of the prism A is 4 inches and each base edge of prism B is 6 inches. That's telling us our similarity ratio, our A-B ratio, is 4 to 6 or 2 to 3. Okay. The volume of prism B is 135 cubic inches. Find the volume of prism A. Well, volume is an A to B ratio. It's an A cubed to B cubed ratio. What is A cubed to B cubed? 2 cubed to 3 cubed, or 8 to 27. That has to equal volume of prism B is 135 cubic inches. So prism B is the larger one, so that comes from the 6 inches. So it's got to be at the bottom here. 135 cubic inches over volume of prism A. Okay. Cross multiply, or just multiply both sides by 135. The volume of prism A is equal to 8 over 27 times 135. And 8 times 135 divided by 27. Volume of prism A is 40 inches cubed or cubic inches. That's example 7. And this type of way of solving these problems is going to show up a few times in this unit. Example 8 is a composite solid. It's more than one solid either put together or, in this case, subtracted. Okay, we have a cylinder with a triangular based prism hole cut out of it. Okay, and the triangular base is an isosceles 10, 10, 12 triangle. Okay, we want to find the volume of this solid. So to find the volume of this solid, we're going to find the volume of the cylinder, and then we're going to subtract the volume of the prism. So the volume of this solid is equal to the volume of the cylinder minus the volume of the prism. Okay, so let's find the volume of each one. Let's off to the side here, find the volume of the cylinder. So the volume of the cylinder, area of the base times the height. Area of the base. So we have down here that the radius is 10 centimeters. So the area of the base is 100 pi centimeters squared, times the height, 32 centimeters. So 3,200 pi centimeters cubed. I'm going to leave that in terms of pi for now, because I'm going to be subtracting something that's not going to have a pi in it. So eventually I'm going to multiply by pi, but for now I'm going to leave it in terms of pi. Let's find the volume of the prism. again, equals area of the base times the height. Area of the base is the only part of this problem that's a little bit tricky. So I've got some space down here. Let me draw this 10, 10, 12 triangle. What I don't know, I could do Heron's formula to find the area of this triangle. I don't want to do that. Can, because it's isosceles, do this. 6 something 10, it's Pythagorean triple. 6, 8, 10. The area is 1/2 8 times 12 times the height of the height of the prism, which is the same as the height of the cylinder, 32. 4 times 12 is 48 times 32 gives me 1,536 centimeters cubed. So the volume of our solid is 3,200 pi minus 1536 centimeters cubed. That's the exact answer, and if the question on the quiz or test says exact, that's what we're going to do. If it says leave in terms of pi, that's what we're going to do. If it says round, then we'll go into the pi key. So 3,200 times pi key minus 1536 gives us 8,517.1 centimeters cubed. That's example 8. All right. Lateral area, surface area, volume of a prism and a cylinder. Okay. Lateral area of a prism, perimeter times height. Lateral area of a cylinder, circumference times height. In my opinion, these are the exact same formula. Lateral area, the distance around the base times the height, is lateral area. Surface area for a prism and for a cylinder is lateral area plus 2 times the area of the base. That doesn't matter if it's prism or cylinder. This is one formula. Volume for a prism and cylinder, we've seen a bunch of times in this unit, area of the base times the height. These are all your formulas, fairly simple and easy to remember. In my opinion, there's really just 3 of them because these are essentially the same, 2, 3 formulas. Okay. Example 9. Refer to the diagram and complete the chart. When appropriate, leave the answer in terms of pi. So we have these different shapes here. We have a rectangular-based prism, triangular-based prism, a cylinder, and a cone. Now, I know that we haven't talked about the cone, so I left the cone off of the chart here, and that comes up in a future unit. But where I took this picture from, I didn't want to just cut off the cone picture. So we're really just doing these 3, okay, for this unit. So area, perimeter of the base of the rectangular prism, 4 plus 2 plus 4 plus 2, 12 centimeters. For the triangular prism, 3 plus 4 plus, do we know what this is? 3 plus 4 plus 4, I think. 3 plus 4 plus 4? Yeah, because this is 4, right? This is 4 here. So 3 plus 4 plus 4, or 11 centimeters. And perimeter of the base of the cylinder, circumference of the base, or 10 pi. And this is also centimeters. Okay, area of the base. Area of the base, 4 times 2, 8 centimeters squared. Area of this base. So it might look like this is a right angle here and this is a 3, 4, 5, but it's not. It's 3, 4, 4. And we're told that the height of this triangle here is actually 2. So 2 times 4 divided by 2 is 4 centimeters squared. And area of this base is 25 pi centimeters squared. Lateral area. Lateral area is perimeter of the base times the height of the prism or cylinder. Okay, so 12 times 6, 11 times 6, 10 pi times 7. So 12 times 6, 60, 72 centimeters squared. 66 centimeters squared. And 70 pi centimeters squared. Surface area is equal to 2 times the area of the base plus the lateral area. So 16 plus 72, so 72, 80, 88 centimeters squared. 8 plus 66, 74 centimeters squared. 50 plus 70, 120 pi centimeters squared. Volume, area of the base times the height. Area of the base times the height. Area of the base times the height. So 8 times 6, 48 centimeters cubed. 4 times 6, 24 centimeters cubed. 7 times 25, buck 75, 175 pi centimeters cubed. Okay. Question 10. Facts about base and height of the prism are given. Sketch each prism and find its lateral area, surface area, and volume. So an equilateral triangle with side 8 and height 10. Difficult to draw. At least difficult for me. 8 by 8 by 8, height 10. So lateral area. So let's do perimeter first. Perimeter is going to be 24 units. Okay. Area of the base. I'm just going to go down the list that we did up here because it makes things pretty easy. Area of the base. So off to the side here. I have an 8 by 8 by 8. This is 4. So 64 minus 16. So Pythagorean theorem. C squared equals A squared plus B squared. 64 equals A squared plus, or H squared plus 16. 64 minus 16 is 48. So square root of 48. Square root of 48. 224. 212. 2, 6, 2, 3. So 4 square root 3. I knew that because it's 60, 30. Silly. 4 square root 3. Sometimes you don't see the obvious. So the area of this base is going to be 16 square root 3 units squared. And lateral area. Lateral area is perimeter times the height, so 240 units squared. Surface area is equal to 240 plus 2 times this, so 240 plus 32 square root 3 units squared. And volume is equal to area of the base times height, so 160 square root 3 units cubed this time. So lateral area, surface area, volume. Triangle, so a triangular prism with sides 6, 12, 15, height of 10. So 9, 12, 15, sorry. 9, 12, 15. That's a 3, 4, 5. Makes it a right triangle. Height of 10. So perimeter equals 9 plus 12 plus 15, 21 plus 15, 9 plus 12 plus 15, 36 units. Area of the base. So like I said, 9, 12, 15 is a 3, 4, 5, so it has to be a right triangle. So base is 9, height is 12, 9 times 12 divided by 2 is 6 times 9, or 54 units squared. Lateral area is perimeter, lateral area is perimeter times the height. So LA is equal to 360 units squared. Surface area is equal to lateral area plus 2 times the area of the base. So this is 108 plus 360. So 360 plus 108, 468 units squared. Volume is area of the base times the height, or 540 units cubed. Isosceles triangle with 13, 13, 10, height of 7. So we're back to this type of a drawing. 13, 13, 7, 10 is the third one. So perimeter, 13, 13 is 26, 36 units. Area of the base. Okay, so 13, 13, 10. When I put in the height, 5, 12, 13, Pythagorean triple. 12 times 10 is the same thing as 6 times 10 or 12 times 5. Either way, it's 60 units squared. Okay. Lateral area. Perimeter times the height. So 36 times 7. 252 units squared. Surface area. Lateral area plus 2 times the area of the base, so 120 plus 252 is 372 units squared. And volume is area of the base times the height. So 6 times 7 is 42, so 60 times 7 is 420 units cubed. Isosceles trapezoid with sides 10, 5, 4, 5, and the height is 20. So I'm going to try and draw it this way. So 5, 4, 5. Height is 20. This is 10. There's our isosceles trapezoid. Perimeter. 10 plus 10 is 20, 24 units. Area of the base. Area of the trapezoid. 1/2 base 1 is base 2 times the height. 1/2. 4 plus 10 is 14 times the height. Well, the height we don't have, so we're going to have to figure it out. So, I don't have room over here. 5, 4, 10, 5. Draw this down. That means I've got 4 here, which means I've got 6 for the outsides, which means I've got 3 and 3. 3 blank 5. The height is 4. 3, 4, 5, triple. So half of 14 is 7. Height is 4. 28 units squared. So the area of the base is 28 units. I don't know why I wrote cubed on the perimeter. Squared. Lateral area. Perimeter times the height, so 480 units squared. Surface area is lateral area plus 2 times the area of the base, so 456, 480 plus 480, 536 units squared, and the volume is area of the base times the height, so 560 units cubed. There's example 10, A, B, C, and D. 11. So a drinking trough for horses is a right trapezoidal prism. So you can see the trapezoid at the ends. Shown below, if it is filled with water, how much will the water weigh? If 1 cubic meter of water weighs 1 metric ton. So something we need to notice is that not all of these units are in meters. This one is. I'm going to change all of these into meters and not centimeters like some of them are. Okay, so this is going to become 1 meter, 0.4 meters, 0.5 meters, 0.5 meters, and 2 meters. Okay, so meters cubed, 1 meter cubed is equal to 1 metric ton. So we need to find out how many cubic meters of water we have. That's volume. Volume equals area of the base times the height. So we're going to find the area of the base. Area of the base is equal to the area of the trapezoid. 1/2 base 1 plus base 2 times the height of the trapezoid. 1/2 base 1 is 1, base 2 is 0.4, and we're going to have to figure out what the height is. So this is half 1.4 times the height, okay, or 0.7 times the height. So what's the height? This is 0.5, 0.5, 1, and I'm sorry, 0.4. I flipped it upside down, and 1. That's down. So if this is 0.4, And that means I have 0.3 and 0.3 left over. Just like in the previous problem, it's a 3, 4, 5, only it's 0.3, 0.4, 0.5, the height here. Half of 1.4 is 0.7 times 0.4. 0.7 times 0.4 is 0.28 meters squared. The volume here is 0.28 times 2. 0.28 times 2 is 0.56 meters cubed, or 0.56 metric tons of water. Example 12. Find the weight of the steel I-beam shown below. Steel weighs 7,860 kilograms per meter cubed. So we got to find how many cubic meters this I-beam is, the volume of this I-beam in cubic meters. This is 10 meters. These are all in centimeters. I need to change them to meters. 0.3, 0.05, 0.2, 0.05, and 1.25. Sorry, I went the wrong direction. 0.125 meters, 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 meters. Okay. Different ways we can do this problem. We can find the volume of the entire prism and subtract out these two prisms. We can find the volume of this top part times 2, add it to this middle part. We could go this direction. There's all sorts of different ways that we can do it. I'm going to do this top part times the bottom times 2 because it's the same as the bottom part. And then I'm going to add in this middle part here. Okay. So let's find the volume of the top part is going to be the area of this rectangle right here. Okay. So we'll call that volume 1. So volume 1 is 0.05 times 0.3 times 10. 0.05 times 0.3 times 10. 0.05 times 0.3 times 10. 0.15 meters cubed. That means volume 2 is also 0.15 meters cubed because this is the second one. Okay? Volume of the third one, volume 3, equals. So I know it's 0.2 high. How wide is it? So this is 0.3 minus 0.125. Yeah, times 2, right? 0.3 minus 0.125 minus 0.125 gives me what's left here. So this is going to be 0.2 times 0.3 minus 0.125 minus 0.125 gives me 0.05 times 10. The height. So 0.05 times 0.2 times 10 is 0.1 meters cubed. So the volume of the beam is equal to volume 1 plus volume 2 plus volume 3, or 0.1 plus 0.15 plus 0.15 gives us 0.4 meters cubed, and times the weight times 7,860 kilograms per meters cubed. Notice the meters cubed are going to cancel here, something we saw earlier, times 7,860 gives us weight equals 3,144 kilograms. That's the weight of this steel I-beam. Example 13. A diagonal of a box forms a 35-degree angle with the diagonal of the base. As shown, use trigonometry to find the volume of the box. Well, we know it's a 6 by 8 by something. We'll call this H. H is what we're going to have to find. Okay, so we know it's a box. We know this is a right angle. That's 6. 6 by 8, 3, 4, 5, 6, 8, 10. Okay, so this diagonal of the base is 10. I need to know the height of the box, the height of this rectangular prism, and that is H is over here, 35 is here. I know the 10, tangent 35 degrees equals H over 10. H is equal to 10 tangent 35 degrees. H is approximately 35 tangent, approximately 7.00, and we don't have any units here. So our height is about 7. So our volume is equal to 8 times 6 times 7. 336 units cubed, approximately. All right, 14. Judging by appearances, what is the surface area of each solid? These are probably the hardest problems, or the trickiest problems to do, because what parts of each of these composite figures are on the surfaces that we're going to need to calculate. So a few different ways we're going to do this. We can find the area of this bottom base here. We can find the area of this part around. We can find the area of this left face. Got to find the area of this top half of a sphere, lateral area of the cylinder, sorry. And we're going to find this semicircle and this semicircle, and then add up all those pieces. And there's no easy way, quick way to do it. That's just the way that you've got to do it. Okay, so let's take a look at this bottom here. This is an 8 by 7 square. I look at this part of it, it's 8 by 7. So we'll call this area 1, 8 by 7, or 56 centimeters squared. This is one of our semicircles. We're going to actually have 1, 2, 3, 4 of these, because there's another one over here, just like it. So we'll call this area 2 but we're really going to do 4 of these times 4 times 2 times 2, because each pair makes a circle. Together this makes a circle. Together this makes a circle. Okay, so the radius is 3.5, so 2 times 3.5 squared pi, or 3.5 squared, 12.25 times 2 is 24.5 pi centimeters squared. So that's each of the semicircles. Okay, what do we have to do now? Well, there's a rectangle here. Call that area 3. That's 4 by 7. 28 centimeters squared. There's a rectangle here, which is 4 by 8, and there's 2 of those. So there's another one in the back here. So 2 times area 4 is 2, 4 times 8. 4 times 8 is 32, 64 times 8. Yep, 64 centimeters squared. What do we have left? Well, we have the half of a cylinder here and half of a cylinder here. Unfortunately, they have the same radius, but they do not have the same heights. So I can't just add them or make one cylinder out of them. So this cylinder here, this half of a cylinder, area 5, would be half. Circumference is 7 pi, and the height is 4. So 14 pi centimeters squared. Same thing in the top here, we have half, area 6, half. Circumference again is 7 pi, only this time the height of this cylinder at the top is 8, or 28 pi centimeters squared. So the surface area for this shape is all of these added together. 1, 2, 3, 4, 5, 6 added together, so 56. 56 plus 28 plus 64 equals 148 plus, let's add the ones that have pi's in them, 24.5 plus 14 plus 28 equals 66.5 pi centimeters squared, or approximately, times pi plus the 148, approximately, so I'm going to fit it in here, 356.9 centimeters squared. Part B. This one's a little bit easier. In fact, it's a lot easier, because this half of a cylinder and this half of a cylinder make a full cylinder. So if I find the surface area of this cylinder combined, and I'm going to add it to the 4 faces, the front, the back, the top, and the bottom, not the left and the right of this prism. Okay, so the surface area of the cylinder is equal to lateral area plus 2 times the area of the base. Lateral area is going to be circumference times the base. The circumference is 8 pi times height, which is 3, plus 2 times area of the base. So the radius is 2, so 4 pi. So 24 pi plus 8 pi is 32 pi meters cubed. So that's the surface area of that cylinder. I'm going to add to it 6 times 3, which is 18 times 2, 18 squared, 6 times 4, 24 meters squared, another 24 meters squared. So add to this plus 18 and 18 is 36 meters cubed plus 48 meters cubed. Surface area of the whole shape, let's see, 36 plus 48, 84 plus 32 meters, 32 pi, sorry, 32 pi meters cubed, or approximately 32 times the pi button, that's 84, approximately 184.5 meters cubed. Part C. Part C, we've got this curved eye-type shape. Okay, let's find the easy ones. Area 1 times 2, because it's going to be front and back. Okay, so area 1 is going to be 32 times 3 times 10, or 30, or 60 inches squared. Okay. You know what? No, that's how I'm going to do it. Area of the eye. So area 2 times area 2, because the top and the bottom is going to be area of the square, area of the, well, it's not a square, it's a rectangle. Rectangle minus area of the circle that's formed. So area of the rectangle is 80, 8 by 10, minus area of the circle, radius is 4, so 16 pi times 2 times 2. So 160 minus 32 pi inches squared. And then we have the lateral area of this cylinder that we need to add in. So area 3 is the lateral area of the cylinder. The lateral area of the cylinder is circumference of the cylinder times the height. Well, the circumference is 8 pi, and the height is 3. So 24 pi inches squared. And the surface area is adding these up. So the surface area is equal to 60 plus 160, 260 plus 60, 220. And then negative 32 pi plus a 24 pi is minus 8 pi inches squared, or approximately 220 minus 8 times pi, approximately 194.9 inches cubed. Squeeze that one in there in the bottom. Okay. 15. The edge, so we've seen this figure before in a previous unit. The edge of a large cube is 12 inches long. So this is 12 inches, 12 inches, 12 inches, 12 by 12 by 12. The cube is painted on the outside and then cut into 27 smaller cubes. So it's only painted on the lateral area. Okay, find the answer these questions about the 27 different cubes. How many are painted on all 4 faces? How many painted on 4 faces? None of them. How many are painted on 3 faces? This is painted on 2. None of them. I'm sorry. I reused the picture. Take it back. The cube is painted on the outside. So all 6 faces are painted. I take it back. So even though this one's not, because I used this picture from the previous unit, all of the faces of the original cube are painted. Okay, so take it back. How many are painted on 4 sides? There's still none painted on 4 of the sides. How many are painted on 3 of the sides? This is painted on 3 of the sides. Any that is a corner. 4, 5, 6, 7, 8 corners. How many are painted on 2 sides? Well, the middle edges, right here, here, are painted on 2 sides. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 are painted on 2 sides. How many are painted on 1 of the faces? There's 1 on each of the centers of the cube, so there are 6. And how many are painted on 0 faces? There's 1 in the center of this cube that is painted on none of the faces. Okay, what's the total surface area that is unpainted? Okay, well, there aren't any that are painted on 4 of the sides. There are 8 that are painted. So, all right, total surface area that is unpainted. So let's go through these. 8 of them are painted on 3 of the sides and not painted on the other 3 sides. So there's 8. And what are these? So they're 4 by 4 by 4. They're 4 inches by 4 inches by 4 inches. So there are 8 of them painted on 3 sides. There are 12 of them painted on 4 sides. There are 6 of them that are painted on 5 of the sides. And there's one of them that's painted that is not painted, sorry, unpainted. Unpainted, unpainted, unpainted. And there's one of them that is unpainted. On 6 sides. Okay, so each side is 4 by 4, or 16. So there are 8 of them. 3 sides, and each side is 16 inches squared. 12 of them, and on 4 sides, each side 16. 6 of them, 5 sides, 16, and one of them, 6 sides, 16. So 8 times 3 times 16, 84 inches squared. 12 times 4 times 16. 768 inches squared. 30 times 16. 480 inches squared. And 6 times 16. 96 inches squared. Add all of these up. 96 plus 480 plus 768 plus 384 equals 1,728 inches squared unpainted. For part B. Sample 16. A pipe is 2 meters long and has an inside radius of 5 centimeters, an outside radius of 6 centimeters. How many cubic centimeters of pipe metal in the pipe? Metal are in the pipe. Okay, it's 2 meters or 200 centimeters tall. Okay, so the volume of the outside cylinder minus the volume of the inside cylinder. So I'm going to write total volume is equal to volume outside minus the volume of the inside. So volume of the outer cylinder, area of the base times the height. Okay, area of the base. So the outer cylinder has a volume, area of the base. The radius is 6, so 36 pi times the height, which is 200. 36, 7,200. 7,200 pi centimeters cubed. Volume of the inner cylinder, again, area of the base times the height. Area of the base, this time the radius is 5, so the area of the base is 25 pi. And it's still a height of 200. So 5,000 pi, 25 times 200 is 5,000. Centimeters cubed. So total volume or volume of the pipe. Let me change this. Volume of pipe. Volume pipe is equal to 7,200 pi minus 5,000 pi, or 2,200 pi centimeters cubed, or approximately 2,200 times pi key, approximately 6,911.5 cubic centimeters or centimeters cubed. That's example 16. Example 17. A cylinder has been cut from the cube. Find the volume of the remaining solid. Round your answer to nearest tenth. Okay, so volume of the solid is equal to volume of the cube minus the volume of the cylinder. Volume of the cube is equal to 6 cubed. 6 cubed, 36 times 6, 216 cubic inches, or inches cubed. Volume of the cylinder is area of the base times the height. Area of the base, so the diameter is 4, the radius is 2, area is 4 pi, and the height is 6. 24 pi inches cubed to cubic inches. 216 minus 24 pi inches cubed. 216 minus 24 times pi key equals 140.6 cubic inches or inches cubed. Example 18. The outside diameter of a pipe is 5 centimeters. The inside diameter is 4 centimeters. The pipe is 4 meters long. What is the volume of the material used for this pipe length? Round your answer to the nearest cubic centimeter. This is identical to this problem, only we've changed the 6 and the 5 to a 5 and a 4. And this is not 2 meters, it's 4 meters or 400 centimeters. So, centimeters, 5 and 4. So 5 there. Everything else is the same. So volume of the pipe is equal to the volume of the outside minus the volume of the inside pipe. Volume of the outer pipe is equal to area of the base times the height. So the outer pipe, the area of the base, the radius is 5, the area is 25 pi times 400. 25 times 4 is 100 times 100, it's about 10,000 pi centimeters cubed. Volume of the inner, still area of the base times the height. The area of the base, this time the radius is 4, so the area of the base is 16 pi, again times 400. 16 times 400 gives us 6,400 pi centimeters cubed. Volume of the outer is 10,000 pi minus volume of the inner, 6,400 pi centimeters cubed. We're going to round this to the nearest cubic centimeters. We're going to round, so 10,000 minus 6,400. That's 3,600 pi centimeters cubed, approximately, times pi key. 11,000, this is going to round up, 11,310 cubic centimeters when we round that up. Example 19. The radius of cylinder B is twice the radius of cylinder A. The height of cylinder B is half the height of cylinder A. Compare their volumes. Okay, so we have cylinder A, cylinder B. B is the shorter one, but wider. This is B. Okay. If this is R, then this radius is 2R. If this is H, then this height is 2H. Okay, and I think that's going to make things easier for us instead of dealing with fractions. Let me make sure I did it right. Radius of cylinder B is twice radius of cylinder A, and the height of cylinder B is half of the height of cylinder A. So that makes things. If I could make this an H and make this an H over 2, I think I just want to avoid the fractions. Compare their volumes. So volume of A, area of the base times the height. Area of the base is R squared pi times the height. So R squared pi times the height, 2H. So 2R squared H pi units cubed. That's a volume for A. Volume for B, again, area of the base times the height. Area of the base this time is going to be 4R squared pi, 4R squared pi, and the height is 2, is just H. So we get 4R squared H pi. Volume B, cylinder B, volume of cylinder B, volume of cylinder, volume of cylinder B is twice the volume of cylinder A. Example 20. Are all spheres similar? Yes, just like all circles. Are all cylinders similar? No. Are all cubes similar? Yes. All right, two similar square prisms have base areas of 4 meters squared and 36 meters squared. Find the ratio of the heights. I'm giving you the A squared to B squared ratio. All right, so I'm telling you the A squared to B squared ratio is 4 to 36, or 1 to 9. What I'm looking for is the ratio of their heights. That's the A to B ratio. The A to B ratio then is 1 to 3. And there's the answer to part A. Part B, if the height of a larger prism is 27 meters, what's the height of the smaller prism? So we know they're in a 1:3 ratio. So height of the smaller over the height of the larger, which is 27, has to be in a 1:3 ratio. Multiply both sides by 27. The height of the smaller one has to be equal to 9 meters. 21. Scale factor. I'm saying scale factor, and again, I should say similarity ratio. Apologize. So similarity ratio. Similarity ratio is 3 to 4. Ratio of the bases, 3 to 4. Ratio of the lateral areas is going to be 9 to 16. Ratio of the surface areas, 9 to 16. Ratio of their volumes, 27 to 64. 4 cubed is 64. Okay. 5 to 7. No matter what, these two rows are always going to be the same. These two rows are always going to be the same, and they're the square of these two rows. And this row is going to be the cube of these two rows. It's 5 to 7, 25 to 49, 25 to 49, and 125 to, I don't know, 7 cubed, 343. Okay, 2 to 1, 2 to 1, 4 to 1, 4 to 1, 8 to 1. 16 to 81, 16 to 81. I can't go directly from this to this one, but I can go from this one to these. 4 to 9, 4 to 9, and then I can go from here to here. 64 to 9 cubed, 729. Okay, 4 to 9, 4 to 9. 2 to 3, 2 to 3, 8 to 27. Okay, again, 8 to 125. I can't go to these ones, but I can go to these two directly. Cube root of 8 is 2. Cube root of 125 is 5. 2 to 5. 2 to 5. Square those. 4 to 25. 4 to 25. Two similar square prisms have volumes of 48 centimeters cubed and 162 centimeters cubed. The surface area of the larger prism is 135 centimeters squared. We want to find the surface area of the smaller. So by giving you the two volumes, I'm giving you the ratio of their volumes, right? I'm giving you the A cubed to B cubed ratio. It's 48 to 162. Okay, 48, 162. Oh, no. By 6, 7. So this reduces down to by 6, 27 and 8, right? 48, 6. Yep. So they both reduce by 6 down to A cubed to B cubed is an 8 to 27 ratio. I'm looking for areas. I'm looking for the A squared to B squared ratio, which is going to equal the larger one's 135, so that's on the bottom, 135, and surface area of the unknown one, the smaller one, is on the top. Okay, I don't know the A squared to B squared. I know the A cubed to B cubed. Just like in this previous problem, we go from A cubed to B cubed to A to B, which is going to be 2 to 3. Making the A cubed to B cubed squared, sorry, I knew the cubed. squareds to be equal to 4 to 9. 4 to 9. Multiply both sides by 135, so the surface area of the smaller prism is equal to 4 times 135 divided by 9, 60 centimeters squared. 23. Another similar problem, no pun intended. Two similar cylinders have a lateral area of 8 square feet and 18 square feet. Find the volume of the smaller cylinder. The volume of the smaller cylinder is 32 cubic feet. Find the volume of the larger cylinder. So I'm giving you this time the a squared to b squared ratio. A squared to b squared ratio is 8 to 18, or 4 to 9. I need the a cubed to b cubed ratio, which is going to be the 32 over the volume of the larger one, the unknown larger one, we've got to find. So the a to b ratio, again, is 2 to 3, like in the previous problem. So the a cubed to b cubed ratio, 8 to 27. This is equal to 8 to 27. Cross multiply. 8 times the volume of the larger is equal to 24 times 30, 720. Divided by 8, volume of the larger, divided by 8, it's going to be 90 cubic feet, or feet cubed. 23. Problem 24. Some stories say that Paul Bunyan was 10 times as tall as the average human. Assume that Paul Bunyan's bone structure was proportional to that of ordinary people. Strengths of bones is proportional to the area of their cross-section. How many times strong as the average person's bones would Paul Bunyan's bones be? Well, if he was 10 times tall, okay, that's the A to B ratio is 1 to 10. So the A squared to B squared ratio, area, is 1 to 100, meaning Paul Bunyan's bones would be 100 times stronger. Okay. Weights of objects made of like materials, so these are both bones, are proportional to their volumes. How many times the average person's weight would Paul Bunyan be? So A cubed to B cubed ratio would be 1 to 10,000. 10 cubed. So Paul Bunyan's weight would be 10,000 sorry, not 10,000, 1,000. 10 cubed. One too many zeros. 1,000. 1,000 times heavier. Okay. Human bones can support about 6 times the average person's weight. Use your answer in parts A and B to explain why Paul Bunyan could not exist with the bone structure that was proportional to that of ordinary people. Well, 6 times he's 100 times stronger. Okay, that's 6 times 100. He can hold his weight. His weight is 1,000 times the weight of an average person. But his bones can only support 600. Right? 6 times that. He can lift he's 1,000 times stronger. His bones can lift 6 times their weight. 600 times the weight. He'd get crushed under his own weight of his own bones. He'd be crushed under the weight of his own body, which does actually happen to actual giants. They typically are in a lot of pain and crushed under their weight. And that's the end. Thank you very much. Bye.